This lab deals with the motion of an object that has constant velocity, or in other words, traveling in the same speed without changing direction. I recorded a toy car rolling across a table and used Newton's second law to help me predict the motion of the car. We use Newton's first law to assume that there are no net forces acting on the car, which gives it a constant velocity. As the tracker data shows, the car is moving in the positive x direction. The graph on the right shows the change in position in regards to time. The graph shows that near the end of the video, the car is starting to slow down and not maintain the constant velocity due to the slight curve in the data. I used VPython to make a computational model to represent the predicted outcome of the data. I used the tracker data to input initial conditions into my VPython code. This is shown here. I used the first 3 data points in tracker to find the velocity by dividing position over time. In my loop, I then wrote code to update the velocity and position over 0.668 seconds, which is the amount of time the car was moving in my video. I used the momentum principle to solve for final velocity, which is equal to initial velocity plus the net force divided by the mass of the object times delta t. Because we were observing constant velocity, the net force was 0, meaning that our initial velocity will be our velocity calculated in the loop as well. I used the formula to update position, which is the final position is equal to the initial position plus the ball's velocity times delta t. When the code is run, you can see that a ball is moving in a straight line across the y-axis at a constant velocity. A graph is also plotted, which shows the linear change in position of the ball over time. As you can see in this graph, the data plotted by VPython on the red line shows the object moving in a straight line and slightly farther than the observed data. This could be due to our assumption that there were no net forces acting on the car. Comparing these two graphs shows that there must have been some net force acting on the car. This could possibly be friction from the table on the tires of the car or drag from the air. If I were to reverse the axes, the graph would look fairly similar to the data that I originally had in tracker. However, the amount the graph went up in the y-axis would be the same every frame because the time interval was constant, and then the data points along the x-axis representing position would get closer together as the car started to slow down. Theoretically, the graph shouldn't change if you reverse the axes because both intervals were constant if we were calculating constant velocity. In this lab environment, it would not be possible to calculate all of the pushes and pulls so that the net force equals 0. Because I had no way of quantifying how much force I was pushing and in turn how much drag and friction were occurring. There was also no way for me to consistently pull the car back to wind up the spring throughout the different times I filmed to be able to come up with one consistent data point for how much force the car was released with. If I were to run this experiment again, I would possibly use a larger object that moved a little slower so that it would be easier to pinpoint the center of mass. I also think that I would have gotten much more accurate results if I used something where I knew the velocity was controlled, like a remote-controlled car instead of a pullback car.